Welcome back, everybody. In this section, we're going to talk about the resting membrane potential. We're doing it now because physiology books tend to talk about it when they talk about the cell. But not to worry, when we come back and we talk about the nervous system, we'll be hitting some more details of it again. So let's go ahead and get started. And the first thing I want to do is refresh your memory where different ions are located. And you understand that normally there is a greater concentration of potassium inside the cell and a lower concentration outside the cell. So it would passively diffuse out. And the opposite is that there's a lot more sodium outside the cell than there is inside the cell, so it will passively diffuse into the cell. But the sodium-potassium pump puts them against their concentration gradients, but we're not going to be talking about the sodium-potassium pump. So let's just talk a little bit of physics, okay, because of the words that are used. An electrical potential. So this is the difference in charged particles between point A and point B, okay? And this difference in charge is a potential energy. And this potential energy can become kinetic energy and produce a current. And all a current is then is the flow of these charged particles going from point A to point B. And we measure that in volts. You're used to the word volts when you're talking about your electrical power lines are going into your house or the voltage of a certain appliance. Well, in the body, we're really talking about millivolts, okay? And if it's a potential voltage, it is polarized because it's not where it needs to be yet. And so in a cell, we measure it across the plasma membrane. So this is a typical setup where you have a little threshold detector at one side attached to a voltmeter. And then you have a little microelectrode, because we're talking plasma membrane, and it goes across the entire plasma membrane from the extracellular space into the cytosol. As you can see, this one is reading a minus 70 millivolts. Okay. And that is what we call the resting membrane potential. When the cell is at rest, what is the charge difference between outside and inside, or the charge difference going across the plasma membrane? Okay. So the extracellular fluid is set at 0, okay? And then once that's set at 0, then the probe reads what it is inside the cell. And at rest, that example, and which is typical, is a minus 70 millivolts. And that's what we see in the cytoplasm of our neurons. And that's why when you are looking at pictures that show nerve impulses or action potentials traveling down, they always talk about how the inside of the plasma membrane is negative compared to the outside of the plasma membrane. And it is, it's a minus 70 millivolts in charge difference. So a negative value means there's more negatively charged particles inside the membrane, because that's where the reading is being done, because the outside was automatically set at 0. If the voltmeter was reading positive, that would mean there would be more negatively charged particles outside that cell. So why is the resting membrane potential of a neuron minus 70? Well, there's 3 different factors that come into play. Diffusion of ions down the concentration gradients, okay? There's some selective permeability, so some ions can cross easier than other ones. And then there's also some attractions of cations to anions. But let's talk specifically about the 3 ions in play here. The one that has the most influx, surprisingly, is potassium. It is 40 times the concentration inside the cell as it is outside the cell. And of the 3 different ions we're talking about, the plasma membrane is most permeable to potassium, so it diffuses through. Do you remember when I talked earlier about leakage channels that open and close, and they can be open most of the time? Well, there are a lot of leakage potassium channels. So it's easy for it to move down its gradient and go outside the cell. Now, yes, some potassium can re-enter the cell, and if left alone all the time, it would eventually reach equilibrium, but it doesn't. But just the fact that the potassium is so much more concentrated inside the cell than outside the cell, if we measured just the influence of potassium, we would have a resting membrane potential of -90. But as I said, it's -70. And so the biggest influence to get it from -90 to -70 is sodium, where, as you know, the vast majority of the sodium is outside the cell, and it's being attracted to the inside of the cell because of that negativity inside the cell. But as opposed to having freely leakable channels where millions of potassium ions can travel per second, only thousands of sodium ions can travel per second. So it's a mere trickle in comparison. And so it only reduces the voltage by 20 millivolts, bringing it up to almost -70. And the last influence, which is very small, is that sodium potassium pump, where we're sending 3 sodiums out for every 2 potassiums in, and and in the nervous system, this is 70% of the energy of your neurons that can produce. And that's why your neurons have a constant need for glucose and oxygen 24/7, even when you were asleep. And that's why neurons are the cells that die the fastest in your body when you have problems with your circulation. At most, this would change the millivoltage 2 to 3 millivolts. So it's mostly potassium with some influence from sodium. All right. So when we have a voltage change, we have a triggering event and the ion channels are open and the sodium rushes in. That first part is called a local potential. It is a short range. It is very local. So that incoming sodium only diffuses out a little bit along the inside of the plasma membrane. Yes, it creates a little current that spreads out, but it's not going all over LA County. It's just staying like in your bedroom area, that sort of thing. Okay. And it dies out. And as it's moving further and further away, if you look at the tracing, the bottom left, you can see the impulse is getting lower and lower and lower until the point where the impulses are sub-threshold and won't cause anything to happen. So the characteristics of these local potentials are that they are graded. In other words, the bigger the stimulus, the bigger the potential, the bigger change in voltage, because the bigger the stimulus, the longer that ion gate channel is going to stay open, and then more ions can rush through it, thereby giving you a bigger voltage chain. And they also can do summation, as I've talked about summation earlier, and we also have summation going on in lab. So hopefully you understand that concept fairly well. The second of 4 characteristics is that they are decremental, meaning from the point of origin, that is the strongest. And the further out you get, the weaker they get. And this is because sodium is leaking back out and potassium's reversing the flows. And so eventually long distance, there's 0 effect that's happening. The third effect is if the stimulation stops, this is reversible. Okay, with no stimulation, the cation diffuse out of the cell quickly returns the voltage back to the resting membrane potential. And the fourth characteristic is we always talk about these things being excitatory because they are getting you closer to the threshold, so you're being less negative. But these can either be excitatory or inhibitory. They can either increase or decrease the resting membrane potential. So they can cause depolarization or hyperpolarization. realize, of course, though, 90% of the time we are going to be talking about depolarization. All right. So I mentioned a moment ago the threshold potential. So what is a threshold potential? Well, in the neuron, let me just give you a number, it's minus 55. So what does that mean? If the resting membrane's at minus 70, it means somehow that membrane has to depolarize 15 millivolts, 15 up to minus 55. And at minus 55, that's where you can get an action potential. If it doesn't, you won't. It's that simple. Okay. Anything that depolarizes it, that keeps it more negative than minus 55 is called a subthreshold stimulus. And what's interesting, all you have to do is have a stimulus big enough to get you to minus 55. If you have a stronger stimulus, you still only are going to have the same action potential. It's kind of like when you go to like the Santa Monica Pier and you're taking the little mallet and you have to ring the bell at the top. All you have to do is ring the bell. If you ring the bell louder, you don't get 2 prizes, you still just get the 1. Okay. So if we don't reach the threshold in the neuron of minus 55, no action potential. Okay. So if we meet or exceed the threshold, if we get up to minus 55 or even more positive than that, then we have an action potential. Where this is going to happen is where we're going to have a lot of voltage gated channels. If you only have the random voltage gated channels, the chances of this happening are going to be a lot less. And so we have these areas where we have 10 times the concentration of the channels per micrometer. So when we look at the action potential, it is represented by this red line. Now I know in the past it just goes up and it comes back down and everything's hunky-dory, but it's actually not like, oh, immediately we're up there. There's a lot of little nuance going along in here. So the first thing that happens at threshold is as soon as you hit the minus 55, and here you can see going from the minus 70 to minus 55. Okay. In that first part, do you see there's a little slope up there? That's because we've got some sodium channels open leaking, but as soon as we hit that minus 55, they all go woof. Okay. And what's interesting is actually potassium gates are going to start opening at the same time, but they don't go woof. They just go, they're very, very slow to get to where they need to go to let calcium out. Okay, so we have these sodium gates wide open. So we're going to have a rush of sodium entering the cell, millions of ions per second. And that's going to further depolarize the membrane. And that gives us that steep upward curve on the graph. Okay, the more channels that are open, the more sodium rushes in, the more rapid the rise is. Now, as it passes 0, that voltage actually inactivates the sodium channels and they start closing, but they don't go all woof all at the exact same time. They close slower than they open, so that we actually shoot past a neutral 0 millivolts and actually go up to about a plus 35. Okay. So once we're greater than 0, we know our polarity is reversed. Those slowly opening potassium gates are now fully open by the time we have reached the peak of plus 30. And so potassium is rapidly exiting the cell, and that's going to cause a rapid repolarization or rapid downward spike. Now, as you recall, the sodium channels are closed already, and now we have potassium channels, but they're open longer than the sodium channels, and so we're having more potassium exit. So we don't actually stop on the dime of the minus 70 millivolt. We actually overshoot the resting memory potential, and this is called hyperpolarization. And we will gradually come back up to the resting membrane potential. So now let's compare the characteristics of this action potential to those we had earlier of the local graded potential. An action potential is an all or nothing. Going back to the Santa Monica Pier, if you don't reach your threshold, if you hit it and it doesn't reach the bell and make the bell ring, there is no action potential. There is no winning of a prize. They do not give you one arm of the teddy bear or the teddy bear's head. Okay. But if the stimulus depolarizes and gets all the way up to minus 55 threshold, then the neuron will fire at its maximum voltage. Okay. You can't be halfway pregnant. You can't give half of a voltage. Okay. Above the stimulus, as I said before, a larger stimulus is not going to produce a larger voltage change. As opposed to what we talked about with the local graded potential, action potentials do not get weaker without over time. They do not get weaker the further away they are from the gates. So they are called non-decremental. What this means is as the action potential is traveling down the entire neuron from the axon hillock all the way down to the synaptic knob, this action potential is the same strength as this action potential down at the other end. And the last thing is this is not able to be stopped. It is irreversible. Once it starts, it's going to go to completion all the way down. So that brings us to the concept of a refractory period. A refractory period is a time where it's nearly impossible or it's totally impossible to stimulate that neuron, that area of the neuron again, to get another action potential. You can stimulate a different area of the neuron that's not refractory, but in the refractory zone where the action potential has begun and you've already had your rapid depolarization and you have repolarized and hyperpolarized, you are now refractory, and another stimulus coming in there either cannot or it's really hard for it to generate another action potential. So let's see why that is. We have two concepts going on here. An absolute refractory period means no way, no how, no, absolutely not, ma'am. No stimulus of any strength will ever trigger a new action potential. You are done until the end of the refractory period, absolute refractory period. But the absolute refractory period is then followed by what's called the relative refractory period. And in this area, you're still hyperpolarized. So an unusually strong stimulus can generate a new action potential. So I'll show you that in a moment. So here's the absolute refractory period. And you notice it has to do with the upward, the rapid upward and the rapid downward, when we are still above the resting membrane potential. At this time, the sodium channels are not active at all. Okay. And remember, as we are coming down, as well as we're going up and coming down, potassium channels are still open. So this is the absolute refractory period. It only lasts about a millisecond from the time of from the time you met the threshold, not before the threshold going up to the threshold, but from the time you met the threshold and had the rapid opening of sodium channels until you had the total closure of potassium channels and you went back down to the resting membrane potential. That's only about a millisecond in time. That's the amount of time that nothing can happen. However, there's another few milliseconds, about 3 more milliseconds, that things can happen if they're stronger than normal. And this is the relative refractory period. This is the time when that plasma membrane area is hyperpolarized. So for instance, if you were to say that this straight line is minus 70 and the peak hyperpolarization, let's say maybe it's minus 85, okay? To get from minus 85 to the threshold of minus 55 would mean you would need a stimulus that has to depolarize by 30 millivolts, as opposed to the normal stimulus from the resting membrane to the threshold only has to depolarize 15 millivolts. So at this point in time, you would need a stimulus that was twice as strong in order to depolarize enough to generate the action potential. But if it came along, you would have an action potential there. And that's why it's called the relative refractory period. All right. So once we get to the end of the synaptic knob, then that neuron is going to have a synapse, okay? And we've talked a lot, and you've learned in anatomy about the typical neuromuscular junction where you're releasing a neurotransmitter, acetylcholine, to bind on a postsynaptic cell, and that's called a chemical synapse. But we also have electrical synapses, and we have them between our between cardiac muscle cells. But let me show you the difference between a chemical synapse and an electrical synapse. In an electrical synapse, look at these green things. Do they remind you of those gap junctions, those intercellular gap junctions? Do you see the little opening there, the little connexons? That's because it's exactly what they are. And so you have gap junctions connecting two cells. And so any kind of current flow that happens in the presynaptic cell, those ions can flow directly into the postsynaptic cell almost immediately. This is super simple. It's just flowing down a gradient. Okay, and the response in the postsynaptic cell is going to be the exact same response we had the presynaptic cell, although it might be a little bit lower. This is going to be important for smooth muscle and cardiac muscle, so don't just poo-poo it for right now. It is an important concept. It does happen in some other places, like for instance, if you've ever seen people with eye jerks, the muscles that cause the eye jerks, they do have electrical synapse. And also in our brains, that some neurons involved with emotions and memories work on electrical synapses. So it's important for helping you study your anatomy and physio. So definitely understand them. They're not nearly as complicated as our chemical synapse. And with that, I am done talking about the resting membrane potential and everything that is associated with that. So thank you once again for all your hard work. I really appreciate it, and I will see you at our next video. Bye-bye.